So yesterday we introduced the nonlinear L-functions, as I call them. So when you have G acting on X and you have some Langlands parameter, let me just vaguely write Galois. It could be Veil, it could be into G. Then we defined L phi X to be the sum over all fixed points of phi on X, and this set is assumed discrete. Otherwise, we say the L function has a pole of the corresponding linear L functions, so L phi on the tangent space of X. And I'm still suppressing the points of evaluation. I need to make two corrections to things that I said yesterday. First of all, in responding to a question of errors, I said that when X is, let's say, G mod H, so you're detecting, so for a point to be fixed, the parameter has to land in a conjugate of H. And I said that the question of counting fixed points is like counting the fibers of the base change from H to G. That's only true up to the centralizer of the parameter. So we saw examples where, for example, in the group case, where we had a number of fixed points, of course, the fiber of base change there is just a singleton up to counting orbits. But because of centralizer of the parameters, you had several fixed points. So that's the first correction I want to make. The second correction I want to make is I made an error when I wrote down the fixed points in relate to Spencer's work. So I was talking about the case of restriction of scalars from E over F GLN over UN with dual just GLN squared mod GLN, and then non-trivial action of Galois E over F. And I said that generic parameters have fixed points represented by the cosets of I and plus minus I. That's true, but then I said that when the parameter lands in GLA times GLB inside of GL and diagonal, then I said that you have extra fixed points, and I wrote them as identity A, minus identity B, plus minus identity A minus identity B. But if you notice what I wrote here, its coset is the same as that one. So I should have written here plus minus just the identity. Okay, and then you can do the rest of the calculations. Okay, any questions? All right. Now, we also saw how to geometrize this L function. It was the L sheaf Lx, which was defined as push forward of some dualizing sheaf for the map a map of moduli spaces, G local systems, and here G local systems with a section of the associated X bundle. The point was that the fibers of this sheaf are precisely, maybe up to some cohomological shift, these symmetric powers of well, at least Yeah, so here I'm writing the non-linear case, so fibers, so at least over an important set that today I want to fix a notation, so log G. I'll fix a notation to suggest the subset where over which the set of fixed points is discrete. So what do I mean the set of classical fixed points is discrete? If you think of local systems in the Betti setting or in the et al. Setting in terms of something like Langlands parameters again, except that we restrict to the geometric fundamental group, then again, X sections are fixed points of this parameter. Of course, we already said that you should think of this in a derived way as some kind of derived scheme, but just the classical fixed points, just the actual fixed points, the actual sections, should be a discrete set. That's this open set, which of course it's not evident in the notation, but this depends on X. So at least over this subset, the fibers are going to be the sum over X classical fixed points, so X a section of the associated yeah, so maybe let's say rho in log G. So we associate rho is something like, at least in the Betti setting, corresponds to the restriction of a Langlands parameter to the geometric et al. Fundamental group. So here I'm going to take the set of rho fixed points on X, and then the fiber is the sum of the graded symmetric powers of cohomologies, or of rho on the tangent space of X. So if you take trace of Frobenius, you expect that this recovers this. And again, the formulas that I'm writing here are really true up to cohomological shifts. And here I'm writing cohomologies. You should be thinking about complexes. So you can read more details in BZSV. We don't have the most general description, but enough in order to draw, enough at least to relate the two stories over a good locus. Okay, and so, and of course, implicit in all of that is the duality. So between periods and L functions, numerically, if you have a dual pair Gx and G check X check, and here I'm not talking about the Hamiltonian space. I'm really assuming that you have a dual pair of a G space X and a G check space X check. The Hamiltonian space is going to be the cotangent bundle. So assuming that everything is polarized, then the integral of the period function against automorphic forms should be related in the sense of an Ichino-Ikeda type formula, or in the everywhere unramified setting, to the L-function associated to this possibly nonlinear space and the Langlands parameter of phi. And implicit in that, and this is supposed to be a geometrization of the fact that in geometric Langlands, our conjecture is that the period sheaf matches the L sheaf. And maybe one thing that I didn't say is how do you go from here to here? So here we have a sheaf, here we have to compute an inner product. Well, the automorphic form also should have a Hecke eigensheaf behind it. So there is a way to turn homomorphisms between sheaves into inner products between functions. So let me write this just to make sure everyone has seen it. So there is a formula like this, that the trace of Frobenius on the homomorphism between two sheaves on this side, so these are coherent type, constructible type sheaves. So of course we have to work with etal sheaves to take trace of Frobenius. So the trace of Frobenius on home between, actually the dual of the home between two sheaves is equal to the sum. So these are sheaves on some space. So that our space here would be band G. So this is going to be the sum over all points of band G of the trace of Frobenius on the fibers of F tensor Verdier dual of G. So there is a formula like this. So on the right-hand side, we recognize the integral. So this can be written as the integral over what I was denoting yesterday by brackets G of two functions, the function associated to F and the function associated to the dual of G. So if you wanted to translate a sheaf theoretic statement into an integral against functions, you would have to take, for F, you would have to take, for F, you would have to take the period sheaf. For G, you would have to take some sheaf that is associated to some Hecke eigensheaf that's associated, that produces this automorphic form. And then, or maybe the dual of that. And then this formula would tell you that the inner product can be recovered by calculating homes between the sheaves. Now, homes between the sheaves can be translated to the other side of geometric Langlands. So you would end up calculating homes between the dual sheaves, but the dual sheaf of one is expected to be the L-function. The dual sheaf of the other, since it is an eigensheaf, is going to be something like a skyscraper sheaf. So this here translates to a statement, to a calculation of the stocks of the L sheaf. So this here is related to the stalks of the L sheaf. Sorry, the fibers of the L sheaf, actually. This is coherent type sheaf. So this is related to the fibers of the L sheaf. That's why this matches this calculation here, the relation between periods and L functions. So, so that's the story in the factorizable case. Okay, now, what about the non-factorizable case? So the example that I started presenting last time was, well, that the dual of SON plus 1 mod SON. Let me switch back to Hamiltonian spaces, so I'll put a T star here. So the dual of this is the symplectic vector space, which is the standard representation of SON. Let's say that n is even for simplicity. Standard of SON, tensor standard of SP to n. If this were on the automorphic side, we would be talking about the Veil representation. The quantization of this is the Veil representation. But now this is on the spectral side, and here I should put an n, sorry. So this is now on the spectral side. So what formulas do we expect for period integrals? Well, the Chino-Ikeda-Gross-Prasad conjecture tells you that the period integral over SON of some automorphic form, but squared, should be related to the L function associated to this Hamiltonian space. But we have no conjectural formula for the period itself. Okay. Now, where does the period square come up? The period square comes up, so this comes up in the spectral decomposition of the relative trace formula. A relative trace formula is generally associated to two periods, but you can take the same period on both sides. So the relative trace formula is associated really to some kind of quotient stack, and in this case, we'll take the quotient stack G mod H, when this is G and this is H. I really tried hard to avoid writing G and H up to now in order to not to have to put checks here, but okay. Let's put checks for now and we'll get rid of them when we forget about the automorphic side. So the relative trace formula, there's a relative trace formula associated to this quotient, which basically computes the inner product. So this RTF is basically the inner product of two theta series. And the theta series can vary, but if you want to do everything in the unramified setting, you would be computing the inner product of the period function with itself. And then spectrally decompose this inner product, and that's the periods that you would discover for appropriately normalized automorphic forms F pi. So it's natural from that point of view to understand this formula. It's natural, we said that inner products translate to Holmes, and Holmes of sheaves on one side become Holmes of sheaves on the other side. So it's natural from the point of view of the relative trace formula to ask about, okay, so we don't know what the L sheaf should be in that case, but at least this formula should be telling us something about the endomorphisms of the L sheaf, home from the L sheaf to itself. So this, we don't know L in this case, but this formula should be suggestive of the endomorphisms of the L sheaf, simply because here we're taking the relative trace formula takes home from, like, is the numerical version of, is a function theoretic version of homes of the period shift to itself, up to some dualities that I'm suppressing now. Let's not worry about them. Okay? So, and what does this formula suggest? Well, again, the L function is trace of Frobenius on some cohomology, right? Or exterior powers of some, or exterior graded symmetric powers of some cohomology, okay? So this would suggest somehow that the So, first naive guess is that the endomorphisms of this mysterious L shift that corresponds to the period on the other side should be, just by reading the formula, it should be the L shift associated to M check. Okay, so the fibers of this, and in this case M check is just a vector space, so the fibers of this are symmetric powers of, graded symmetric powers of the cohomology of M check. And let me be very explicit on this open set where the discrete, the fixed points are discrete. Well, fixed points here, this is a vector space. Okay, so when you put it over log G check, it becomes a linear local system. So sections of this, the only way that the sections will be discrete is if the only section is the trivial section, the zero section, right? Because otherwise you can scale sections. So sections is H0 of a local system, so it's a vector space. The only way that this can be a discrete set is if H0 is trivial, okay? Moreover, this is a symplectic vector space. It gives symplectic local system. So by Poincaré duality, it's self-dual. So if H0 is trivial, H2 is also trivial. So over this nice open set, we're only talking about H1, okay? So the fibers of this sheaf are this symmetric algebra, but this symmetric algebra just means the usual exterior algebra of H1. H1, rho is the geometric parameter, M check. Okay, in other words, you are given, let me remind you another way to think about this. So given a local system G check, curly G, you twist it by M, that gives you a symplectic. So this twist, this here depends on the parameter rho. So here we're talking about H1 of this symplectic local system. Okay, and there's no H0 or H2. Yeah, G-check, sorry, thank you. Okay. Yeah, that's what I was trying to avoid, but. All right. Now, this is a sheaf. This is some sheaf of complexes of vector spaces. And it has an obvious algebra structure, the exterior algebra. Okay? So the naive guess would be that at least over this good locus, the endomorphisms of the, we don't know the L sheaf, but its endomorphisms should be the exterior algebra. Okay? The problem is that this doesn't even match the factorizable, the polarizable case. Because in the polarizable case, this would be supposed to be the endomorphisms of some object of the same form, except that here you put the, not M check, but a Lagrangian in M check. Okay? And the exterior algebra is not a matrix algebra. So the naive guess would be that over log G check, endomorphisms of the L sheaf is simply this exterior algebra is a sheaf with fibers, a sheaf of algebras with these fibers. But that's not a good guess because this doesn't look like endomorphisms of some vector space. This is not a matrix algebra. Okay, so but this is this is an algebra with a huge nilpotent ideal. Just take the positively graded part of it. It's not a semi-simple algebra. And its only irreducible representations are just the field. So the quotient of this by the positive graded part. This is an algebra whose only irreducible module is just the field itself. Okay, so I'm assuming that everything on the dual side over an algebraically closed field in characteristic 0. So this is not, if M were polarizable, if M check were polarizable, so M check equals X check plus X check dual, would expect something that looks more like a matrix algebra. So we would expect something like endomorphisms of the exterior algebra of X check. Oh, of H1 X check. So of some vector space, exterior algebra of some vector space. This is a matrix algebra. Okay? This is very different from an exterior algebra. Okay? And here is where the conjecture comes in. So the conjecture is that the formation of the exterior algebra is the correct endomorphism sheaf. So the conjecture is that whatever this L shift might be, its endomorphisms restricted to this good locus are a sheaf of Clifford algebras OM check. So maybe before I say another word on this, let me say a few generalities about Clifford algebras. So, and everything I will say is over K, again, algebraically closed field in characteristic 0. The story is more complicated and more interesting without this assumption. So a Clifford algebra is built out of a vector space V, which is quadratic. So it's endowed with a quadratic form. And this quadratic form, and the Clifford algebra is a deformation of the exterior algebra. So the Clifford algebra of V is defined as the quotient of the tensor algebra of V. Instead of modding out by the relations of the form X tensor X, which you would do for the exterior algebra, you mod out by relations X tensor X minus Q of X. In particular, the Clifford algebra is not graded anymore because this is in degree 2, this is in degree 0. So this is just in the vector space. So the ideal that you're modding out by is not homogeneous, is not Z-graded, but because these degrees are both even, it is Z mod 2 graded. So it still makes sense to talk about even and odd elements. So there's a lot of interesting things that one can say about Clifford algebras. For example, they are the basis for constructing the pin groups and the spin groups and all of that. So inside of the multiplicative subgroup of the Clifford algebra, there's the general pin group, which is precisely those elements G such that G, which are units, with the property that conjugation by G fixes the copy of V inside of here. So in degree 1, you have V mapping to this. Okay, and inside of here you have the general spin group, which are the even elements inside of the general pin group, and then you have a map to GM, a spinor norm, and you have a diagram like this of inclusions. Okay, but actually, as an algebra, it's very simple. So if dimension of V is even, and again, over an algebraically closed field. So if Q is a non-degenerate of course, Q could be the trivial quadratic form 0, so then you recover the exterior algebra. But if Q is non-degenerate, and then the Clifford algebra, well, I should put Q in the notation maybe, is semi-simple. And in fact, it's isomorphic to a matrix algebra of dimension 2 to the d over 2 if d is even, and a sum of two matrix algebras if d is odd. So what is the suggestion going up to, so in particular in the even case, it has a unique up to isomorphism irreducible module. Okay? So now let's see what is happening here and where the quadratic space is. So we started with a symplectic vector space, and we took its well, we started with a symplectic local system on our curve, and we took its H1. Because this is symplectic, and because of Poincaré duality, this turns out to be orthogonal. So this is orthogonal. This is quadratic, orthogonal. It has a non-degenerate symmetric pairing, okay, because of the degree. Symplectic in degree 1 becomes orthogonal, okay? So this is my quadratic space, and therefore out of this space, which I can call 0, so out of 0, I can build the Clifford algebra. Okay, I'm suppressing the quadratic form now. Okay. Now, what is the dimension of this space? So what is the dimension of this space? Well, we're over the locus where H0 and H2 are trivial, so the dimension will be completely determined by the Euler characteristic and the dimension of this vector bundle, right? So the dimension will be 2G minus 2 times dimension of dimension of M check. In particular, this is an even dimensional quadratic space. So the Clifford algebra is the Clifford algebra of an even dimensional quadratic space. So this has a unique irreducible module. Yes. Did I say something wrong? Should I? Yes. Yes. That's a good question. Yeah, maybe I'm just looking at the even part here. Hold on. Yeah, but this is spin, not pin. Spin, not pin. So actually, I have a construction. Let me do a reality check in the polarized case, and that will. So let's construct the irreducible modules in the polarized case. So, well, and since we are actually over an algebraically closed field, when I say polarized, sorry, construction of the irreducible module. So I can take a decomposition of my space into isotropic subspace. So even in the even case, let's say. So I can take a decomposition of my space into maximal isotropic subspaces. And then I can take a basis, correspond to this decomposition, I can take a dual basis EI and FI. Okay? Then I claim that the module is going to be the exterior algebra of U, where the EIs and FIs act as creation and annihilation operators. By the way, in the Clifford algebra, the relation is EI-FI plus FI-EI is going to be Q of EI-FI, which is 1. Okay, so I can take this module with this being creation and annihilation operators. I.e., EI acts by exterior multiplication, and FI acts by contraction. And you see here the dimension of this is the dimension, so this is dimension 2 to the d over 2. So Wittek, I think we can read off the grading from what I just said, but yeah, so I think we can read off the grading, but let me not do it right now. Yeah. Okay. So let's go back to our story. If the conjecture is true, so what are we saying here? Just to recap. So just to recap, instead of forming the actual L-sheaf of M check and endowing it with this algebra structure, the suggestion is to form a sheaf of Clifford algebras, at least over this good locus. So M check is going to give a sheaf O M check of Clifford algebras over the good locus of log G check. And the conjecture is that, I wrote the conjecture there, that this is the endomorphisms of the unknown L-sheaf. Now, you might think that because the Clifford algebra has a unique irreducible module, that you've solved the problem, that you have described the L-sheaf. But actually, it is unique up to isomorphism, up to scaling. So, in particular, the fibers of this unknown L-sheaf would be the unique would be isomorphic to the unique irreducible module for the fibers of the sheaf of Clifford algebras. But actually this doesn't, just describing the fibers doesn't describe a sheaf. And this is a very important restriction. So this is close to useless if you want to, for example, draw arithmetic conclusions. This isomorphism is only up to scaling. And therefore, this doesn't tell you anything about how Frobenius acts. It doesn't tell you anything about how the stabilizer of a parameter acts. So, leading to ambiguity about action of Frobenius or action of the centralizer in G check of the Langlands parameter or of the geometric Langlands parameter. Just to explain to you how important this ambiguity is, first of all, clearly you cannot say anything about trace of Frobenius without more precisely identifying this sheaf of algebras, of modules. But just to explain how deep this problem is and how interesting it is, let me start speculating a little bit about how this story transfers to the geometrization of local Langlands. So, this is just going to be a remark, but I think that this is going to be a remark that several people in this audience will care about. So, remark, we can imagine the period L-shift duality in the setting of local Langlands for example, in the setting of, how do I put the tone here, to the left or to the right? So in this case, the period sheaf would encode some representation of, so here F is a local non-Archimedean field. So in this case, the analog of the period sheaf would encode functions on x of f as a g of f representation, or at least part of the period sheaf. So, you know, the Bun-G in that case has various strata that correspond to various inner forms of G. So at least partly, it would encode this representation plus other stuff corresponding to other inner forms. And then, sorry? Yeah, not fixed points. I mean with a GF action as a representation of GF. And then the L sheaf would encode answers to questions of distinction. for example, which irreducibles pi admit a non-trivial, so admit a quotient from my representation. You should be able to read this off from the L-sheaf, because the irreducible representations correspond to certain skyscraper sheaves on the spectral side. Now, the L-sheaf would be formed out of something like the Weil group cohomology of the Langlands parameter, right? So, like in the geometric setting, you had the cohomology of a local system. So similarly here, this would correspond to cohomology, so Weil group, some version of Weil group cohomology of local systems. And then over the analog of the good locus, you would not have H0, you would not have H2, you would just have H1, but maybe for reasons that have to do with the local Euler characteristic, even this H1 would be trivial. So for Euler characteristic reasons, the Euler characteristic is 0. Again, one has to be a bit careful about what kind of cohomology one considers, so this is a little bit speculative, but you would expect that this cohomology would be trivial, so its exterior algebra and its Clifford algebra would be trivial. Over the good locus. However, we know from Gann-Gross-Prasad that the question of distinction has a very interesting answer. And that answer depends on the action of the stabilizer of the Langlands parameter. It depends on a certain character that one attaches to the stabilizer of the Langlands parameter. So, given a Langlands parameter, so what I said up to this point, that means that the fibers of the L-sheaf, even if we cannot define the L-sheaf, the fibers of the L-sheaf would be just lines. Okay? But how does the centralizer usually denoted by S sub f sub phi of a Langlands parameter act on these lines? It has to act by a character. And GGP tells us that it acts by a character determined by symplectic root numbers, by epsilon factors. So you see, knowing the fiber, that the fiber is just a one-dimensional vector space is kind of useless for that purpose. One needs to understand what the sheaf is and how does the stabilizer act. And this is a very interesting and deep problem here. I am out of time? No, I started at 9:30, right? Okay. Okay, so that was the side remark, just to show you how interesting the question is. I think at the last day of the week, Friday, Amina will say something that is related to this question also. All right, now let's see. Okay, so I think I have introduced enough of the conjecture to motivate the talk of JU. The talk of JU, however, will also have some local input. So up to now, I haven't said anything about, I talked about period shifts and L shifts, which are global objects. I didn't say anything about the local conjectures. So maybe let me spend the last 20-something minutes to say something about the local story. No, no, because it's not polarized. Yeah, we cannot write down. So. So relative Langlands is a collection of conjectures. Some of them are at the local level, some of them are at the global level. And there is some philosophy of quantum field theories that explains why these conjectures all come in packages. So basically, we view global fields like Q or FQ double brackets T as three manifolds, and to them, a 4D quantum field theory attaches vector spaces such as the space of automorphic functions. Then we have at least in over function fields, we have the geometric part of that story. So we have something like that, which corresponds to, which is the function field of a Riemann surface or of a curve over an algebraically closed field. So these are two manifolds. And to this, we attach categories like sheaves on band G or incoherent sheaves on local systems. And then we have the local fields like QP. Sorry, what did I write here? Sorry. One bracket. So here we have So these are also two manifolds. And then you can take something like that. This is a one manifold. Or FQ is also in one manifold. So, and as you go down the categorical level, so here you would attach two categories. And so on and so forth. Okay, so there is a question of whether this is just philosophical or whether you can do something with it. And in fact, one can do something with it, but one needs, at least, over curves. But one needs to introduce certain structures called factorization algebras that were introduced by Bellison and Drinfeld. And the idea here, I think the idea is already appearing in their proof of commutativity of the Satake, of the geometric analog of the Hecke algebra. So factorization is the idea that, if you have a curve, let's say sigma bar over FQ bar, then all points have neighborhoods that look the same. So every point has a neighborhood isomorphic to the formal disk spec FQ double brackets T, a formal neighborhood. Sorry, FQ bar. What should I erase? Yeah. Here also I should erase the second parenthesis. Sorry. Okay, so that was an example of a global function. So, and the idea is that of factorization is that, well, you can use this to do a lot of things. So, for example, if you have certain categories living from geometric objects over the formal disk, then you can put one category here, you can put another category here, and then you can form some kind of product between the two categories, so give them some product structure by letting the 2 points collide. This is a very important construction in the geometric story. For example, using this construction, Gates-Corey and Nadler, who were the first to introduce dual groups for spherical varieties, proved that sheaves on a spherical variety are an algebra, which of course you don't see at the level of functions, right? There's no way, functions on the group you can convolve. Functions on G spaces you cannot convolve. But the algebra structure is not coming from convolution, but it's coming from fusion, from taking two distinct points and fusing them together, and then taking some nearby cycles factor under this procedure. So there's also something called factorization homology, where if you have a factorizable algebra, you can take some kind of integral of it over the curve and get an object that's associated to the curve. And so in some sense, this sheaf of Clifford algebras should arise as factorization homology of local objects. That's the only thing I want to say about this story, just as motivation. Now let's talk about the local objects. The local objects will be associated to these formal disks, okay? But one thing that is very important in this story and one should keep in mind is that these formal disks are not canonically equal to each other, because this depends on how I choose my formal variable, okay? I have an infinite number of choices in choosing my formal variable, and the most important kind of choices are the ones that have to do with rotation. I can multiply the formal variable by a scalar in FQ star, okay? And that gives you different ways of identifying these disks, and this is important. So, no, yes. So the local unramified question function theoretically so here I'm going to take F to be a local non-Archimedean field. And of course, when I talk about so F over QP or F equal this, inside of it, ring of integers, mapping to FQ. So I'm going to give myself G some reductive group over O. So, and the local and X some nice G space over O. Nice in particular might mean spherical. Then the question is to describe the module, to understand the module S of X of F, G of O. So by S, I use S for CC infinity as a module for the Hecke algebra. Okay? So this is the function theoretic question. The shift theoretic question so in the shift theoretic question, I have to take F to be FQ bar double brackets T or C double brackets T. That means in terms of this quantum field theory analogy, I'm reducing the dimension, so I'm going up one categorical level. So this also contains its own O. And then by abuse of notation, we're going to be writing GO for what is called the arc group of G. This is a group scheme of infinite type with the property that L plus G of FQ is, G of FQ of T. What? And similarly, I'm going to be writing GF for the formal loop group of G. It's an int scheme. It's a limit of schemes, a co-limit of schemes whose FQ points recover the F points of G. So the question is to describe the category of sheaves on Lx mod L plus G as a module category for sheaves on LG mod L plus G, L plus G. Okay, and I said that I will be using this notation, but I didn't use it, so let's denote this by X F mod GO, GF mod GO mod GO. Okay, these are derived categories of schemes. They make sense on certain stacks. They make sense. And we want to describe this as a module category for this. Now, what do we know about this? I'll recall in a moment, but I forgot to say something. Because of this complication that I said before, that the formal disks are not canonically isomorphic, we would also like to describe what happens when we rotate the disks. So that introduces an extra complication, which is that you don't only want to mod out by these subgroups, but you also need to introduce this extra rotation group acting on the whole story. This is a stronger question. You can recover the weaker question afterwards from it. So you can twist by this rotation subgroup and ask about equivariant sheaves with respect to this rotation subgroup. Now, most people in the audience must be familiar with the geometric Satake isomorphism, which tells you that perverse sheaves, GO equivariant perverse sheaves on the affine Grassmannian, this is the affine Grassmannian, GO equivariant perverse sheaves on the affine Grassmannian are a Tanakian category equivalent to the category of representations of the dual group. Okay? So perverse sheaves that I will denote by a heart on this quotient, let me omit for now the, perverse sheaves by the geometric Satake theorem of Mirkovic and Vilonen are equivalent, they have a natural Tanakian structure and they're equivalent to representations of the dual group. So in particular, that means that over a field in characteristic 0, they are a semi-simple category. They admit no x1 between the non-trivial extensions between them. But they do have, inside of the bigger derived category of sheaves, they have x2s. And these x2s and higher x are encoded by the derived Satake equivalence of Bezrukavnikov and Finkelberg. With some ideas going back to Victor Ginsburg, which says that if you want to describe the whole category of sheaves derived category of sheaves, This is equivalent, well, okay, so we have to say what shifts we mean. So, for example, you might want to describe the bounded derived category of shifts here. And then this is equivalent to perfect complexes of modules for a certain algebra, which is the algebra of functions on the dual group, on the dual Lie algebra, on the dual of the dual Lie algebra. So these are functions on the dual of the dual Lie algebra. So in other words, it's the symmetric algebra of GShtukas. But you think of it as a DG ring. So you think of it as a DG as a complex with trivial differentials. So I'm going to put the shearing sign here. So this is the same as symmetric algebra of G, but this is supposed to be in degree, cohomological degree 2. There is a deformation of this story, which is also included in Bezrukovnikov and Finkelberg. And it tells you what happens when you add this rotation. So we know that the symmetric the symmetric algebra of G of a Lie algebra is the graded of its universal enveloping algebra. The enveloping algebra is filtered, and the associated graded is the symmetric algebra of G. So the non-commutative version of this is that the same kind of complexes for the universal enveloping algebra of G. With a deformation parameter that's usually denoted by the Planck constant h. So what this is it's a sheaf of so this is the Riesz family coming from the filtered algebra U of G. So if you have a filtered algebra, you have a continuous family where you deform it to its degeneration. So this is an algebra leaving over. This is an algebra leaving over a one-parameter space, and if you specialize. And again, I have put some shearing here. Okay, so let me finish by just stating the local unramified conjecture of unramified relative Langlands conjecture. So it says that for good and I didn't have time in the end to say anything about the conditions of being hyperspherical and all of that, but for good G spaces X, there is a dual Hamiltonian space M check. So what does Hamiltonian mean? First of all, it's symplectic. It's a symplectic variety. It has an action of G check. And the infinitesimal part of the action can be recovered from a moment map. So it comes with a moment map to G check star, such that well, okay, let me write the bounded Of course, these things, there are some serious complications about how you define them, but let me not worry about this now. These sheaves on unramified sheaves on X of f, so GO equivariant sheaves on X of f, can be identified with perfect modules for the coordinate ring of M check, again sheared. So there is a non-trivial cohomological grading that you have to put on this algebra, and those are supposed to be G-check equivariant, and I'm realizing that I forgot the G-check equivariance everywhere. And here, these are, okay. Yeah, sorry, I didn't actually state this very properly. The way I wrote it is not quite correct. I have to explain what this is. So, yeah, maybe I'll write something slightly wrong on the board, and I'm out of time anyway. Okay, this is the conjecture, and this category here comes with an action of perfect because of the moment map, you can pull back modules for this algebra to modules for this algebra and act on them. Okay, so if you have a module for this algebra, you can use it to tensor it. You pull back to M check and then you tensor. So you have an action of this algebra here. Sorry? Yes, so this equivalent should be compatible with the action of this category unit. Okay. Yeah. Sorry? And the second category also. Yeah, so we haven't written anything about the second category, but there is an obvious deformation here, and I think this is going to show up in Jayu's talks. Okay. Okay, so let me stop here.
Thank you, Yiannis. Is there any question or comment?
Is there anything in number fields which is analogous to the loop rotations?
Not that I know.
Other question?
So going back to the non-factorized, the non-polarized issue, there's also cases like in Walsh-Bourget's formula where you have a non-trivial Galois action and something polarized become, now you get, is there something that can be said?
Yes, I mean, in general, you have an action of the L group on M check, and it has to be polarized for the whole action, yes, not for G check only.
But can something more be said when, in this case, where it is polarized?
I don't think so, no, I don't think so, because you already see in the case of Walsh-Bourget, I mean, this is the base case for Gross-Prasad, right? So you do see that in the non-split case, this is the original work of Tunnel and Saito, where these epsilon factors appeared for the first time. It's as mysterious as the general case.
Is there a question?
Is there a precise relation between the global conjecture and the local conjecture?
Yes, so this is a good question. So it's so one would need some factorizable version of the local conjecture, and then presumably something can be said about the global one, but I haven't understood, and I'm not an expert. So it's a good question, but I don't know the answer. I don't understand it.
So is there any issue with the this
That's right. So there is when M check is polarizable, there's a causal dual description of this, which looks much more like the global conjecture. So it looks like fixed points on some X check. Okay, so that's when M check is polarizable. When it's not polarizable, I don't know how to write a causal dual description.
Is there something you can say about the ramified case with some kind of Pesko-Kavnikov equivalence, like in the spirit of that?
Well, okay, so there are people working on instances of the ramified case. First of all, a guy who is here. So he recently proved the Kazdan-Lustig type isomorphism at the Vahori level for a special case where you have to take M check and combine it with a combine it with a Grothendieck-Springer resolution of G check and make a statement like that. So people are working on this, definitely.
There's a question? It's okay.
Yeah, fine. How much you can recover from M check from the right-hand side of this local conjecture? You can recover everything. So this coordinate ring is actually what had shown up previously in the work of Braverman, Finkelberg, and Nakajima on not just the Coulomb branch. The Coulomb branch is something like the restriction of this to the constant section, but the ring objects that give rise to the Coulomb branch. So if you take if you assume our conjectures and you take the inner endomorphisms of the basic object, which is the constant sheaf on L plus X. Here, the notion of inner endomorphisms is it involves the Hecke algebra, so it involves endomorphisms in terms of the Hecke algebra. Then, so this is some kind of inner version of endomorphism ring. Then you recover the whole ring K of M check. Okay. I stress the inner because actually, if you just take endomorphisms of this, then you recover the invariance of M check. Okay, so basically inner amounts to taking this and acting on it by the Hecke algebra and taking Holmes to itself. This is some, then you recover the whole coordinate ring.
Last question? No? So let's thank Yiannis again.